Ooh, there we go. So today I'm going to go ahead and review the 8.1 material just because it is so dense. And I've got a couple of worked examples, one from 8.2, in fact, two from 8.2. The first one's the traditional method. The second one is the p-value method. Now, the first thing I want to do when I review the Chapter 8 material is I want to go ahead and run through a couple of examples of translating claims and identifying initial claims. So here's a claim. Stat students have an IQ that is greater than 115. So these are the kind of statements you're going to be seeing in Chapter 8 and beyond. There is some sort of claim involved, and we've got to translate this claim into symbolic form. So it's a claim about a mean, the mean IQ greater than 115. So 115, greater than 115 looks like that. I note that this claim does not include equality. That means it's going to be the alternative hypothesis. The flip side, or the complementary case, in the sense of two things that cannot happen at the same time, mean less than or equal to 115, less than or equal to does contain the notion of equality. So I can pull my claim, null and alternative, right from that kind of statement. And I'll remind people that when we write the null hypothesis, formally, we always write it with just an equal sign, even if it comes with one of those. And as I say, we want to identify the initial claim. This statement here is our initial claim. So these kind of things are important. In fact, I've got one more example I'm going to run through quickly also. Claim: the proportion of students who have had COVID-19 is 43%. The proportion is 43%. P equals 43%. Oh, by the way, when you write this out formally, it really doesn't matter whether you use the percentage or the decimal format. Your calculator is going to want decimal format when you finally do get there, though. So the proportion is equal to 43%. That claim is about as clear an indication of equality as we can think of. And now we need to come up with the flip statement, the converse: equal, not equal. So this time, H naught, P equals 43%. The alternative, P is not equal to 43%. And here we have the initial claim. The other thing that we can take from any formal hypothesis test symbolism is the type of test that we look at. Here we're looking at a two-tailed test because the alternative is the not equal. I'll go over these as we run through our examples. Another thing I wanted to mention is the level of significance. The level of significance, we've been working with this in one form or other. Sometimes we use the alpha, sometimes we use the 1 minus alpha. But it's important to understand that for the concept that we present here, the alpha that we talk about is the probability of rejecting a true null hypothesis. In our court case analogy that you may have heard me use before, that's the equivalent of making the mistake of convicting an innocent man. So alpha is that probability of rejecting a true null hypothesis. Common values of alpha, 10%, 5%, 1%, and others. Sometimes no specific alpha is mentioned at all. It is important, though, to note that the researcher is the person who determines alpha. The 5% level is kind of a default, but it can go ahead and take other values as well. It should be stated in every problem you see from me on quizzes and exams, but if there is no alpha stated, you can go ahead and use 5%. That's the standard going rate. Now, what do we do with the alpha? We compare the alpha with the test statistic. Our test statistic is a combination of values. At the end of the day, it's a number, but it's built up from a combination of different pieces. If we're making a claim about a population proportion, like that first written example, we use the Z distribution, and this is our test statistic. If we're making a claim about a population mean, again, that was one of our examples. We use the T distribution, and we use this particular value. Now, both of them contain an aspect from the sample and a piece of the null hypothesis. Sample. Null hypothesis. So that test statistic is kind of a cobbled together fraction. Our calculator will find that test statistic just like it finds the p-value. And then we can go ahead and we can compare the two. And depending on how that comparison comes down, we either keep the null hypothesis or we keep the alternative hypothesis, more or less. There is subtleties there. Now, there are two distinct methods of approaching your hypothesis test. There is the traditional method, and I start with the traditional method and I use it maybe once or twice. I like it because it is very, very visual. You'll see me do an example here in just a few moments. But at the end of the day, in terms of our examples here, the traditional method relies on a visual notion called the rejection region. We'll talk about where that comes from. And it's based on alpha and the alternative hypothesis, and we end up plotting visually the test statistic. Our calculator gives us all the numbers we need. We just have to put them together in the right way. On the other hand, the p-value, that particular method, we compare probabilities or essentially areas. And it's based here again on the test statistic. You've already seen me use that just a few moments ago to get a p-value. And we combine that in some ways with alpha and the alternative hypothesis. And in a nutshell, we can go ahead and this is the important part right here. If my p-value is less than or equal to alpha, I reject the null hypothesis. If the p-value is greater than alpha, I fail to reject the null hypothesis. So it comes down, the p-value method comes down to a comparison between the alpha that shows up in the problem statement and the p-value, which is calculated as an area based on the test statistic and the alternative hypothesis. They both do exactly the same thing. The big boys and girls use the p-value because it is much more straightforward. It's got a little bit less keystroking. And as I say, it comes down to a sort of a simple comparison. That's why we like it as much as we do. And this brings up the topic of test outcomes. Excuse me. Students typically struggle a bit with test outcomes because, well, at the end of the day, from the perspective of the person who does the statistics in the real world, it's a very precise process that needs to be respected. And I'm going to go back to the court case analogy in a moment. But if the outcome is to reject the null hypothesis, what that means is the alternative hypothesis is more likely to be true. In the court case analogy, it means that the level of evidence has risen above the bar by where the jury can come back with a convict verdict. On the other hand, we may fail to reject the null hypothesis. That means the evidence is not strong enough to support the alternative. And notice the idea there. The evidence is not strong enough to support the alternative. We do not look at it as supporting the null hypothesis. In some sense, the null hypothesis is there's nothing really to look at here. There's nothing of interest going on. It's the alternative hypothesis that the researcher is really making the guess about. Very much like not guilty is where every court case starts, and if it ends there, it's as if nothing happened. Whereas the guilty verdict means a particular amount of evidence has been accrued. Notice that we, and this is really important, we never accept the null hypothesis. We just never accept it, okay? New evidence could come to light tomorrow. So it's not about proving one over the other. It's about making sure there's enough evidence that you can reject one of them. It's a subtlety. Now, let's talk a little bit about the actual tests themselves. There are two of them. As I say, there is the traditional and the p-value method. Your text will run through this list in one form or other, but they both tests are very, very similar, but there are some differences. I begin again with the traditional. I'm going to do one of those in just a moment. I write the null and the alternative hypothesis. I identify rejection regions. I calculate and plot the test statistic. Then I identify the test outcome, reject or fail to reject, and then I address the initial claim. 5 steps. The p-value method also has 5 steps. We write the null and the alternative. We calculate the p-value. We compare it with alpha. If it's less than or equal to, we'll reject the null hypothesis. If it's greater than alpha, we'll fail to reject the null hypothesis. In other words, we'll ID the test outcome, and again, we'll address the initial claim. You'll notice that they're very, very similar. The only places they are different is steps number 2 and steps number 3. And by the way, again, this p-value method here, it is a template. It is what we're going to use for the vast majority of our tests. It is what every person who does statistical research will use. So it's a template that's very, very portable. Now let's take a look at an example and figure out exactly how we're going to work one of these. So I made both of these examples very similar to the material in 8.2. So these are the kind of problems you'll see there. Now, let's take a look and read this question, because honestly, everything is in the setup here, because your calculator is going to run through it like water running down a hill, like nothing. So it's got to be pointed in the right direction. So a new COVID drug is being tested for adverse reactions. We have some data. 362 people were tested, 23 people reported an adverse reaction. So at the 5% level of significance, we're going to test the claim that adverse reactions occur in 10% of patients. So there's a lot going on here. First, we have our data. My calculator will know what to do with that when I feed it the data. Next, I noticed that at the 5% level, I have my alpha, 5% level of significance. Now, we're going to test the claim that adverse reactions occur in 10% of patients. P equals 10%. That looks to me like it's going to be the null hypothesis, because I've got an equals there. The complementary event is the proportion is different than 10%. That one does not contain equality. That's the one that will become my alternative hypothesis. So my first example is the traditional method, so you can understand how this actually works and why the central limit theorem plays the vital role that it does. So n equals 362, x is equal to 23, my alpha is 5%. So step number one, H naught, P equals 10%. The alternative, P is not equal to 10%. My initial claim is the null hypothesis. So let me just put a little bubble around that so I don't forget. Now, we'll use the Z distribution, but there's a couple of things I need. I have to take a look at my alternative hypothesis to determine the type of test. That's a two-tailed test. We have the Z distribution, so step number two involves drawing the distribution, the Z distribution, and realizing that with the alpha of 5%, I've got a critical value on the left, I've got a critical value on the right, and this bit of area here and here is alpha over 2. So to get to those critical values, I'll use my inverse norm tool. That's what goes ahead and finds the area based on, the points based on area. So let me go ahead and bring up my calculator. All right, there we go. So let me share that calculator screen. All right, so there's my calculator. Let me clear the screen. I go back to distributions. We have the inverse norm, the area, total area in this case. Oh, I'm going to do it like this. 0.05 divided by 2. The mean is 0, the standard deviation is 1, and I'm going to use the left tail. So This will mimic what anyone using one of the more basic TI-84s would also see. So I enter that in, I hit enter, and oh, it changed it. I'm sorry. Let me try that again. In fact, let me go ahead. Let me try it again. There we go. Negative 1.959, negative 1.9599, negative 1.96. Now, I don't want to belabor the point, but you can actually set that up a number of ways. From my perspective, I've got that negative 1.96. So let me stop my share. And I know that negative 1.96. I know via the symmetry of the graph that if it's a negative 1.96 over there for 0.05 over 2, it's a positive 1.96 over there. So inverse normal with symmetry really goes ahead and gets my critical values for me. Now let's understand exactly what we found. These are the rejection regions. If my test statistic should land in one of those, that's where I'll go ahead and reject the null hypothesis and go with the alternative. If the test statistic lands somewhere in the non-rejection region, as we like to call it, I keep or fail to reject the alternative, the null hypothesis. So there's the test, there's the null and the alternative. There's the critical values and rejection regions. The only thing else I need now is the test statistic. So let me come back to my calculator. So stat over to test. I'll use, and I'll put this on my notes in just a moment, the one prop z-test. So z-test, z-distribution, let's claim about a single population proportion. So the claim was, and this is where, if you take a look, let me go ahead and stop my share for just a moment. This is where I need my null hypothesis. The proportion is claimed to be equal to 10%. I need to remember, once I get into calculator land, I need to actually use the decimal version of 10%. X, well, let's see. There were 23 people out of 362 that had adverse reactions. We had a two-tail test. You can see I have the choice left, right, two-tail, which is why the translation is so important. We'll leave things in blue. We'll just go ahead and calculate. Maybe we'll come back and see what the drawing looks like. All right, so there is my test statistic. I'm going to take 3 decimal places, negative 2.3125313, negative 2.313. So, by the way, there's a p-value there. So there's my z-score. It looks more like a t than a z. There you go. There's my z-score. Now what I need to do is I need to go ahead and plot that relative to this scale here. If I take a close look at that, I can see the negative 2.313. That's more negative than negative 1.96. So when I plot him, he falls in the rejection region. So That tells me what I need to know. So now we reject the null hypothesis. And at that point, in some sense, the test is over, except for the fact that we've got to identify, or I should say, address the initial claim. There's a couple of things that we need to do when we address the initial claim. Here's our initial claim. The proportion was equal to 10%. Well, we're going to reject that. So at alpha equals 5%, data support, excuse me, data do not support H naught P equals 10%. So that gives you all three steps. You have step number one, or excuse me, all five steps. You have step number one, writing the null and the alternative. Step number two, finding the critical values in the rejection regions. Step number three, calculating and plotting the test statistic relative to those rejection regions. Step number four, interpreting the result. So we reject H naught because of where that test statistic landed. And step number five, at the alpha equals 5%, data do not support alpha, excuse me, H naught equals P equals 10%. You'll notice that this guy right here is the initial claim. That guy right there. That's the one that was written into the problem to begin with. So let me go ahead and run through one more example. The wording, the wording will change a bit from problem to problem. So here we're going to use the data to test the claim that more than 15% residents have used a rideshare service. Use a 1% level of significance. 152 people were surveyed and 31 people had used a rideshare service. So there is the statement. We have a claim more than 15% of residents. P equals greater than 15%. So there's my, looks to me to be the alternative hypothesis because it does not contain equality. The flip side of that is P is less than or equal to 15%. That will be my null hypothesis. One other thing we need to pull from the statement. A 1% level of significance. So my alpha is 1%. So this time I'm going to use the p-value method. And I cannot stress this enough. The p-value method is the preferred way of doing these problems, not the traditional method, the p-value method. And I'll show you why when I'm done with this one. So n is equal to 152, x is equal to 31, alpha is 1%. Let's see, more than 15%. So H naught P equals 15%. H1 P is greater than 15%. In this particular case, let me put a fluffy little cloud around my initial claim. So that's step number one. All right. And at that point, we're actually ready to go right to the calculator. Capital P. This is a lowercase p. This is an uppercase P. It does matter when you read it. Your calculator absolutely sucks at presenting the difference. So let's see what Mr. Calculator says here. All right, stat. Back over to test. Down to the one prop z test. 0.15 is the claim for the null hypothesis. That's the 15%. X was 31. N was 152. This was a right tail test. We'll go ahead and calculate this. There's my test statistic, and right below the test statistic is the p-value, 0.03125, 0.0313. So my calculator is done. I'm done using my calculator. I'm back over here. And again, what was it? One prop z test. So that's how I got that little guy there. Now, I need to compare that with, and I always write my alpha on the left, excuse me, my p-value on my left and my alpha on the right. Alpha was 1%, 0.01. Which number is less or less than or equal to? This number is smaller or bigger than this number. This one is bigger. 3 cents is bigger than 1 cent every day of the week. So the p-value is bigger than the alpha. I'll remind you that when the p-value is bigger than the alpha, we fail to reject the null hypothesis. Let me write that again. Let me write out the final little bit now. Notice my initial claim was the alternative. Did we go with the alternative here? No, we did not go with the alternative. We're sticking with the null unless new evidence comes to light. So at alpha equals 1%, data do not support H1P is greater than 15%. So that is the entire hypothesis test when we use the p-value. Number one, we wrote the null and the alternative hypothesis, identifying the initial claim. 2, we calculated the p-value. And then in 3, we compared it with alpha. We made a determination based on that comparison, and we addressed the initial claim. So that's really what it comes down to. And here again, I'll remind people that when p is less than or equal to alpha, we reject H naught. When p is, strictly greater than alpha, fail to reject H naught. So we got to keep that in mind when we run through that step there. And it's an important step because I want to add a follow-up question. So here's the follow-up question. redo the problem with alpha equals 5%. So I've changed the level of significance. I'm the researcher, I can do that. I'll note that if I redo the problem, the data didn't change, so the p-value is still 0.0313. The data didn't change. The null and the alternative hypothesis didn't change. Once I've got my p-value, I compare it to the one thing that did change, alpha. This time the alpha is 5%. 0.0313 is distinctly less than or equal to 5%, specifically less than. If you put less than in, you're totally right. So less than or equal to 5%, so that means I reject the null hypothesis. Now, I'll remind you that this guy here was our initial claim. So, because I've rejected the null hypothesis at alpha equals 5%, data do support H1, the proportion is greater than 15%. The outcome of the test in terms of reject versus fail to reject changed. It changed because we went from a 0.01 level of significance to a 0.05 level of significance. So at the end of the day, we can make the observation all other things being considered, a larger alpha makes it easier to reject the null hypothesis. All right, easier to commit a type 1 error. Remember, alpha is the probability of rejecting a true null hypothesis. So in other words, whoops. So a larger alpha makes it easier to commit what we call that type 1 error. All right, I'm going to go ahead and stop the recording.